Take a close look at a map of the world, and the coastlines of South America and Africa appear to be designed for locking together. In the early 20th century, however, this was dismissed as nothing more than a curious coincidence. Alfred Wegener proposed that these continents were actually moving, a theory he called continental drift. His peers were quick to point out a physical reality that seemed to make the idea impossible. Oceanic crust is denser and more rigid than the rock making up the continents. To Wegener's critics, a continent trying to move across the ocean floor was like a wooden ship trying to plow through solid ice. There was also the problem of the seafloor itself. If the oceans had existed for billions of years, they should be buried under miles of sediment raining down from the water above. Yet when geologists measured the accumulation, they found only about 300 million years worth of debris. The rest of that geological history was missing. Harry Hammond Hess spent the Second World War as a captain in the U.S. Navy, but his background was in geology. While cruising between battles in the Pacific, Hess used his ship's echo-sounding technology to map the deep ocean floor, searching for clues in the uncharted terrain. Hess realized the ocean floor was a mobile conveyor belt. He proposed that magma oozes up from mid-ocean ridges, creating crust that spreads outward, carries the continents, and sinks into oceanic trenches to be recycled. This seafloor spreading accounted for the missing sediment, but at the time, Hess lacked the mathematical evidence to prove the Earth's crust was actually in motion. Evidence of this movement is captured the moment new rock forms at a divergent boundary. As magma rises and cools, iron-rich minerals fall below their carry point, about 580 degrees Celsius, and lock in the direction of the Earth's current magnetic field.
Researchers discovered parallel stripes of normal and reverse magnetism, shown in alternating yellow and white. These bands are identical on both sides of the magma source. This symmetry proves the seafloor acts as a geological tape recorder, preserving every magnetic flip as rock spreads outward. This creates a global conveyor belt. New crust is generated at the ridges and eventually pulled back into the mantle at subduction zones. This mechanism, known as slab pull, keeps the total size of the Earth constant even as new floor is continuously created. By calculating the age of these magnetic stripes, scientists could finally measure the exact speed of the continents, though modern measurements would eventually reveal a discrepancy in the data. Today, space geodesy allows us to track the movement of tectonic plates with millimeter precision using a network of GPS satellites. While these satellites confirm the plates are moving, the seismic record doesn't seem to account for it. When scientists calculated the total energy from every recorded earthquake along these boundaries, the numbers didn't add up to the physical distance the plates traveled. A 2026 paper published in Nature provided the explanation. For the first time, researchers used deep-sea observatories to witness a massive seafloor spreading event as it happened. Along the southeast Indian Rift, the ridge axis suddenly failed, allowing magma to violently tear through the crust. In just 16 days, enormous dikes injected 150 million cubic meters of magma into the new fractures. During this event, the ridge cooled apart at 5 centimeters per minute, nearly 500,000 times its average speed. This single burst achieved decades of spreading in a matter of days, proving that tectonic movement relies on sudden, rapid leaps rather than a slow, steady creep. These tectonic fractures serve as the architects of extreme biological ecosystems. Along the mid-ocean ridges, hydrothermal vents act as underwater hot springs, pumping mineral-rich fluid into the freezing deep. While these vents have been studied for decades, a recent Schmidt Ocean Institute expedition looked deeper. Using an underwater robot, scientists overturned chunks of volcanic crust to see what was happening beneath the surface. They found a complex world thriving inside the dark volcanic cavities, teeming with chemosynthetic bacteria, snails, and giant lead and white tube worms. Inside these cracks, the water is a steady 75 degrees Fahrenheit, creating a protected subterranean habitat. For years, researchers were stumped by the lack of tube worm larvae in the open water above the vents. The evidence now suggests these animals use the warm fluid highways beneath the surface to travel through the crust and colonize new territory. Tectonic shifts are more than a mechanical process. The planetary engine that moves continents is the same one harboring hidden life in the deepest wounds of the Earth.